From the fantasy of science fiction to the routine of everyday life, circular motion affects all of us, whether at work or at play. At the fairground, going around in circles can be fun, even if it's a little scary. There's certainly a lot going on here, but what is actually happening to move me around in this way? How can I be certain that I won't fall out when I loop the loop?
Of course, it involves the forces acting and the accelerations they produce. But what are the forces involved in all this, and what can we say about the acceleration experienced by a particle moving around in a circle? And how can we model the motion mathematically? Well, the first question to consider is just what does happen when a particle moves around in a circle?
The key point is that every particle that moves in a circle experiences an acceleration, even if the speed is constant. Why is this? Well, before we can think about acceleration, we first need to consider velocity. The direction of the velocity vector is always tangential to the circle. And what about the length of the velocity vector? Well, that's just the speed. The faster the particle goes around the circle, the greater the length of the velocity vector. And the more slowly the particle moves, the shorter its velocity vector becomes. Now, what about the acceleration? Well, it's natural to suppose that if the speed is constant, then there's no acceleration. But that isn't so. Remember, acceleration is the rate of change of the velocity vector. So, every change in the velocity produces an acceleration, even if it's only the direction of the velocity vector that is changing. So, even when the speed is constant, there must still be an acceleration. But when the speed is changing as well, there are two sources of acceleration, one due to the change of speed and another due to the change in direction. So, how can we express the velocity and acceleration mathematically? Well, to specify the position of a particle moving in a circle, we need to know two things. One is the radius of the circle, that's r, and the other is where the particle lies on the circle. We can do that by specifying an angle theta. R and theta are the plane polar coordinates of the particle. Now, what about its velocity? Well, to find the velocity, we need to know both its magnitude and its direction. And the direction is easy. It's tangential to the circle. The magnitude of the velocity is the speed of the particle. That is, the rate of change of its distance around the circle. And the distance the particle has gone is the length of this arc, which is r times theta. For theta increasing, the speed is just r times theta dot.
So now we know everything we need to know about the velocity. We know its magnitude, r theta dot, and its direction, which is tangential to the circle. But what we don't know is how to write it down in symbols. And to do that, we need a unit vector which specifies its direction. In other words, a unit vector tangential to the circle. Here it is, and we're going to call it e theta because it's nice to think of it as a unit vector in the direction of increasing theta. While we're about it, we might as well have another unit vector in the direction of increasing r, and we'll call that one ER. So here we have a pair of unit vectors which are at right angles to each other. So ER and E theta are in some ways like the Cartesian unit vectors I and J, but the great difference is that these ones move. As the particle moves around the circle, these two vectors rotate. And this fact is going to play a very important part in our argument. Now, we introduced E theta in the first place so that we could write down the velocity in symbols. So what is it? It's just r theta dot times E theta. Well, so much for the velocity, but what about the acceleration? Well, the obvious thing to do to find the acceleration is to differentiate our expression for v. To do that, we'll need to know the derivative of E theta, and that's why it's important to remember that ER and E theta are changing. But it's not obvious, unfortunately, what the derivative of E theta is. What we do know, though, is that it must be closely related to the derivative of ER, because the two are fixed together. And as it happens, we can work out the derivative of ER from what we've done already. The particle's position vector is just the radius r times the unit vector er. If we differentiate that expression, we're going to get the velocity again. The radius is constant, so the derivative is just r er dot. But we already know the velocity. It's r theta dot e theta. So er dot must be theta dot e theta. The thing to notice about this formula is that the direction of er dot is at right angles to er, and its magnitude is given by the angular speed of rotation. How does that help us to find e theta dot? Well, e theta is rigidly connected to er, and the two rotate together. They're related in the same way, whatever the radius of the circle. er and e theta are rotating at the same rate, so the magnitude of e theta dot is the same as the magnitude of er dot. The only difference is in their direction. The direction of e theta dot will be at right angles to e theta. That is, it's in the minus er direction. So e theta dot is minus theta dot er. Here are the results we've already established: the derivatives of er and e theta, and the expressions for the position and velocity. So what about the acceleration? Well, that's v dot, so we need to differentiate again. And this time we have to differentiate a product of a scalar, r theta dot, times a vector, e theta. We differentiate that just as though it was an ordinary product. And we get a is r theta dot e theta dot plus r theta double dot e theta, which, using this result for e theta dot, becomes a is minus r theta dot squared er plus r theta double dot e theta. So we have two components of acceleration. The first one points radially inward, and this is the one which corresponds to a change in direction of the velocity vector, and which we have even when the speed is constant. I think of this term as arising from the fact that as the particle moves around the circle, its velocity vector is constantly being turned in towards the center of the circle. And then we have this term, which is along the tangent, and which corresponds to a change in speed. So here are the basic results which are needed to solve any problem involving circular motion. In the rest of the program, we're going to look at two applications. Our first problem is concerned with the motion of artificial satellites. As you know, they can be used for communications. And if a satellite is used for communications, it's convenient to put it in what's called a geostationary orbit. That's an orbit where the satellite is always above the same place on the Earth's surface. Of course, the satellite isn't really stationary. It's just going around the Earth in a circle at the same rate as the Earth is rotating around its axis. What we want to ask is, are there any restrictions on the orbit of a geostationary satellite? And in particular, how high above the Earth does it have to be? So, let's start modeling the circular motion of a satellite. Tom?
You can see from this model that if the satellite's going to follow a stationary orbit above some point on the Earth's surface, then its axis of rotation must coincide with the Earth's axis. And its period of rotation must be the same as the Earth's period. But are there any other restrictions on the orbit? Well, the motion of the satellite is circular, so its acceleration is directed towards the center of its circle of rotation. But since there is an acceleration, there must be a force causing it. What is that force? Well, in this case, the force is due to gravity. So, what is the force of gravity? This is another of Newton's laws. It's the law of gravitation, and it says that there's a force of attraction between the satellite and the Earth. There are three parts to the definition. Firstly, the force is directed towards the center of the Earth. Secondly, it is proportional to 1 over r squared, where r is the distance of the satellite from the center of the Earth. And thirdly, it's proportional to m, the mass of the satellite. That is, F equals km over r squared, where k is a constant. So that's the force of gravity. Now, the important thing to note here is that the force is directed towards the center of the Earth. How does this affect the geostationary orbit of this satellite? Well, so far we know that the motion is restricted to circles of latitude. So the acceleration of the satellite is towards the center of the circle. But the force causing it, gravitational attraction, is towards the center of the Earth. So there's only one possible orbit, an equatorial one. So we know the orbit is around the equator, which leaves us with just one more question. What's the height of the satellite above the Earth? To answer that, we need to use the other part of the law of gravity, and in particular, we'll need to find k. I'll do that now. Well, at the surface of the Earth, we know that the gravitational force equals mg. So we have km over r squared equals mg, where r is the radius of the Earth. So rearranging the equation gives k to be just g r squared. Substituting 9.8 meters per second squared for g, and 6.4 times 10 to the 6th meters for r, that means that k is approximately 4 times 10 to the 14th meter cubed per second squared.
Here's the Earth and the satellite. Newton's second law tells us that force is mass times acceleration, and the force is km over r squared. Because the force is radial, we're only concerned with the radial component of acceleration, and that's r theta dot squared. So we have this result. Now, we want to find r, the radius of the geostationary orbit. So the first thing to do is to get an expression for r. The m's here cancel, and we can multiply through by r squared. If we rearrange this equation, then we get r cubed is equal to k over theta dot squared. Now we can work out theta dot from the period of the satellite. We know that it takes a geostationary satellite just 1 day to go around its orbit. So if I call that time t, theta dot is just 2 pi over t. Substituting for theta dot in here gives us this result. Now we're nearly there. T is 1 day, that's roughly 8.6 times 10 to the 4th seconds. And k, well, we found that out earlier, it's about 4 times 10 to the 14th meter cubed per second squared. Putting those values in this equation gives r is 4.2 times 10 to the 7th meters. Now Tom's question was about the height of the satellite above the surface of the Earth. So finally, subtracting the Earth's radius, the satellite must be 3.6 times 10 to the 7th meters above the Earth. That's roughly 22,000 miles. This problem was quite an easy one. Since the speed was constant, we only had to use one part of the acceleration equation. So now, how about a harder one? Tom?
This is the Cobra at the West Midlands Safari Park. Why doesn't the car fall down? Or the people fall out? How does something like this get designed to be sure it's safe? Well, as before, it can be explained by looking at the forces involved and the resulting accelerations. But this time, the problem is more complicated because the speed is not constant. Here's a model we can try our physics on. I can release this model car from rest at some height and see what happens. Well, you see, if it's not going fast enough, it won't make it around the loop. But if I release a car from higher up, it enters the loop with more speed and actually completes the loop. Now that's the question we want to consider. From what height here do I have to release the car so it just makes it around? We want to build a mathematical model to predict this, and then to compare with experiment. For our model, let's suppose the loop is a perfect circle, and we'll suppose that the track is pretty well frictionless. So we'll ignore all forces of friction, including air and rolling on the track. So we have to consider only the force of gravity down, and the reaction that the track exerts back on the car. That is, so long as the car hasn't fallen off. Mike.
This circle represents the loop in the track, and here's the car on it. We'll model the car as a particle and locate its position by the angle theta, measured from the bottom of the track. We're going to apply Newton's second law, so we'll need to know the forces on the car. There are just 2 forces. The weight of the car, mg, which acts vertically down, and a force of reaction, whose magnitude I've called r. And I've drawn this force pointing to the center of the track. That's because we're assuming there's no friction, so the reaction between the track and the car is perpendicular to the track. Now I'm going to use the acceleration in polar coordinates. Here's the formula which we derived earlier, and r here is the radius of the track. The acceleration of the car is going to have components in both the radial and the tangential directions this time, because the car's speed will certainly vary. To use this formula for the acceleration efficiently, we'll need to express the forces in terms of their radial and tangential components. That's easy for the reaction. It's already in the radial direction. And we can resolve the weight into its components mg cos theta in the ER direction and mg sine theta tangentially. And so the expression for the total force in terms of ER and E theta is this. The minus sign in front of the R is there because the reaction is towards the center of the circle. And the minus sign in front of the mg sine theta is because its direction is in the minus E theta direction. So now we equate the force with m times the acceleration. And this gives us a vector equation, but we can separately equate the coefficients of ER and the coefficients of E theta to give two scalar equations. That's just the same sort of process that you go through if you've been using Cartesian components rather than polars. So I finish up with these two equations, which involve the angle theta and the reaction force R. And this is my mathematical model. Now that I've got a mathematical model, I can use it to solve the problem we started off with, which was concerned with whether the car would loop the loop. In other words, whether it will get to the top of the track without falling off. Notice that we're not really interested in the details of the car's motion. We don't have to find an explicit formula for theta in terms of t. Much more important for our purposes is to devise a test for when the car falls off the track. We get such a test by thinking about the reaction, R. So long as the car is in contact with the track, R is positive. R can certainly never be negative. So the crucial question is whether R can become zero, because if it does, at that moment the car leaves the track. So I want to find out whether for some angle theta, R becomes zero. And to do that, I have to find an equation for R in terms of theta alone. That is, I have to eliminate the derivatives of theta. The way to do that is to integrate the second of these equations, just once, to obtain an expression for theta dot, and then eliminate theta dot between the two equations that result. So I'll explain briefly now how you integrate this second equation. That involves using a trick. The trick is actually quite a useful one to know, although the details of how it works in this particular case aren't actually very important. The trick is to multiply the equation through by theta dot, because then both sides become derivatives. The left-hand side is the derivative of a half mr theta dot squared, while the right-hand side is the derivative of mg cos theta. So by integrating, we obtain this equation, where c is a constant. And if this looks familiar, that's just because it's the conservation of energy. So next, we have to express the constant c in terms of some recognizable quantity. And I'm going to express it in terms of the speed of the car when it comes onto the loop at the bottom of the track. The value of theta is 0 there, and the speed is r theta dot, which I'll call u. So this gives us c is a half mu squared over r minus mg. And the equation finishes up like this. So now we have two expressions for theta dot squared, one involving r, the other not. The next step is to eliminate theta dot squared between them. Multiply the second by 2 and add, and we get this equation. And rearranging this last equation, we get an expression for capital R. So now we do have an equation for capital R in terms of theta, and u, that's the car speed as it begins the loop. And this equation holds for as long as the car stays in contact with the track. While that's the case, R can't be negative. So, Tom, does that answer your question?
Well, not yet. For one thing, I don't know what u is. In any case, what I really wanted to know was how high up I need to let go of the car so it just makes it around the loop. So I want this height, not the speed with which the car starts the loop. On the other hand, I can work out a connection between u and the height h by conservation of energy. If the car is released from rest up here, its speed down here will be given by a half mu squared equals mgh. So now you should be able to express r in terms of h rather than u.
Okay, so a half mu squared is mgh. So if I put 2 mgh for mu squared in here, I get this formula for capital R in terms of h and theta. Now, we're interested in whether there are any values of theta for which capital R becomes 0. If there are none, so that R is positive for all values of theta, the car remains in contact with the track and is able to loop the loop. So let's look at the graph of this function of theta. I've chosen a particular value of h here, which isn't large enough for the car to loop the loop. We just have a cosine curve with its maximum r at 0 and 2 pi and its minimum at pi. And that's translated upwards by an amount that depends on h. This curve gives the value of capital R in terms of theta, so long as r is positive. So that's just the thick portion of the curve. In this case, the car will remain in contact with the track until theta reaches the value where the curve first crosses the theta axis. Then capital R becomes 0 and the car falls off. If I increase h, the graph is higher up and the route moves closer to pi. Finally, there comes a value of h for which the graph just touches the axis where theta equals pi. For this value of h, the car can just make it to the top of the track. For any larger value, the graph never cuts the axis at all, capital R is positive for all theta, and the car loops the loop. So the crucial value of h is the one for which the curve just touches the theta axis. That's the value for which r equals 0, where theta equals pi. The value of h I want is got by putting capital R equals 0 and theta equals pi in here. Cos pi is -1, so this gives minus 5 mg plus 2 mgh over r is equal to 0. That is, the height we want is 5 over 2 r, 2.5 times the radius of the loop. For this value of h, the car should just loop the loop. For any larger h, it should certainly do so. But that's according to our mathematical model. How does it work out in practice? Tom?
Of course, in practice, we've got to worry about friction. And friction always makes things worse. So one thing we do know from this model is that we will certainly need to release the car from at least 5/2 r up. Well, let's try it. Here's a rule, and here's 5/2 r. Well, it falls off. Now, I've played around with this model, and I've found that the car just makes it around if it's released from here. Let's try that. So, this extra bit of height here is just the amount we need to overcome friction. The next thing to do with the model would be to take friction into account, and that is actually possible. Well, so much for the mathematical model, but I actually found that riding on the Cobra was another matter entirely. Safe as houses.